I think in the interest of time, we'll go ahead and start. So welcome to the distinguished lecture today at the Penn State Center for Socially Responsible Artificial Intelligence. Most of you know about the center, but those of you who don't, it's a university-wide center supported by about 10 colleges and a few of our institutes, as Social Security Research Institute and ICDS, the Computational and Data Sciences Institute. Our speaker today will be Dr. Philip S. Yu. Dr. Yu is a distinguished professor and the Wexler Chair in Information Technology at the Department of Computer Science, University of Illinois at Chicago. Before joining UIC, he was at the IBM Watson Research Center, where he built a world-renowned data mining and database department. He's a fellow of the ACM and the IEEE. Dr. Yu is the recipient of the ACM SIG-KDD 2016 Innovation Award for his influential research and scientific contributions on mining, fusion, and anonymization of big data. The IEEE Computer Society's 2013 Technical Achievement Award for pioneering and fundamentally innovative contributions to the scalable indexing, querying, searching, mining, and anonymization of big data. And the Research Contributions Award from the IEEE International Conference on Data Mining, commonly known as ICDM, in 2003 for his pioneering contributions to the field of data mining. Dr. Yu has published more than 1,300 refereed conference and journal papers, cited more than 138,000 times. He has an H-index of 172. He's applied for more than 300 patents. He was the editor-in-chief of the ACM Transactions and Knowledge Discovery from Data, TKDD, 2011 to 2017, and the IEEE Transactions and Knowledge and Data Engineering, 2001 and 2004. We do several events at the CSRAI, and this is one of the talks on our technical side. It is entitled "A Network Heterogeneity on Graph Neural Networks." So without further ado, I will let Dr. Yu take stage and tell us about his exciting research. Dr. Yu.
Okay, thanks very much for the introduction. So I'm very glad to be here to talk about network heterogeneity, graph neural network. We know graph neural network have been very popular in the last few years, and there are various variations of graph neural networks have been proposed. The assumption of graph neural network is basically the network is homogeneous, and you also have the smoothness property. That is to say, the neighbors share similar feature, context, and labels. But in real world, the real world network or network representation derived from real application are often heterogeneous instead of homogeneous. And in this talk, we're going to look at various types of heterogeneity, including node and link type heterogeneity, neighborhood heterogeneity, fragment heterogeneity, temporal heterogeneity, and structure heterogeneity. And we'll look at how to address these various types of network heterogeneity of graph neural networks. Somehow this screen does not move. Do we have a problem? Okay. So the first thing we're going to talk about is node and link type heterogeneity. So the real network are often heterogeneous. When I say heterogeneous, it means that we can have different node type and different link type. For example, in a publication network, we can have author, paper, and conference. So actually, we can represent this network with a network schema, saying that the author can publish paper, paper can cite other paper, and then the paper can be published in a venue. Similarly, in a computing system, there are all kinds of program or processes being running simultaneously. And you can also use a network schema to represent that, saying that a process can fork another process. It can open an internet socket or access a file. Okay, so you can find the relation between different authors or different processes. So the challenge we need to address to handle a more complicated heterogeneous network is how to preserve the heterogeneous graph structure. The second one is that how to capture the hierarchy of different dependency from simple to complex. And then the third one is how to deal with the different importance of various dependency. So let's go back to the heterogeneous network. So if we go back to the publication network, again, we have this author published paper. The paper can appear in a conference and have a topic. So two different authors, they can be related if the paper they publish have the same, appear in the same conference or is on the same topic. So we can have a meta path connecting these two authors. We can also have more complicated connection, what we refer as meta graph. But in this talk, I used the two terms, meta path and meta graph, interchangeably. Okay. So basically, in this case, the two authors, they published a paper. They are not only on the same topic, they also appear in the same conference. Okay, this one is saying that the two authors, they published a paper, is not only have the same, appear in the same conference, but also share a common co-author. And then there can be also, for example, like a movie database, IMDb, then you can, a movie can have actor, director, and rating. So two movies, they can share the same actor, so they can be connected through a meta path, or they have the same director. Okay? So we can have many examples like that. So basically what we are saying is that for a complicated graph like this, for example, this 1, 2, 3, 4 represent authors, right? And then the green node represent paper, they publish paper. And then the paper can be on the same blue node is a topic or on the same conference, right? So there are many different ways the two different authors can be connected through a meta path. So for each type of meta path, we define a different type of connection between the author. So basically, the original heterogeneous network, once we introduce meta paths, we can reduce the heterogeneous graph into homogeneous graph. For example, if we exploit the relationship P1 that's saying that the authors are connected, if they appear in the same conference, then we get this homogeneous graph, means 1 and 2. They have paper appear in the same conference, so they are connected. P2 means that they are on the same topic. And then P3 means that they are co-author. Okay, so for every meta path, we get a different type of homogeneous graph. So now we map a heterogeneous graph into multiple homogeneous graphs. Okay, so after we decompose this heterogeneous graph into multiple homogeneous graph based on meta paths, then we need to introduce this hierarchical attention. So the first level is the node level attention, because even though all the all the authors now are connected through one particular type of relationship, for example, co-author relationship, but their importance may be different, because if one person co-author with you or with 100 papers, the other author only co-author with you with 2 papers, then certainly these 2 co-authors important are different. And then there are also semantic level attention, because not all the meta parts are equally important. For example, when we talk about co-authorship, that is a stronger relationship then you have another author publish a paper on the same topic. That can be actually quite different. For example, we have 2 authors, they all publish the topic on deep learning, but maybe one paper appeared in ACL, so it's an NLP conference. And then the other author's paper, although it's also on deep learning, but it appeared in CVPR, so it's an image type of paper. So really they can be quite different. So different semantic level or the meta paths can also mean very difference of importance. Okay, so once we have these homogeneous networks, right, we can first do this applying the graph neural network, right, to get this embedding, and then we have to aggregate this through different meta paths, and then we get the final results. Right? So if you can see that the result is much better than if we just apply this traditional graph neural network, when we are fusing these different meta paths together, then we actually will get better results. So this is also applied to clustering, right? So we have better clustering results compared with traditional neural network method. So you can see that here is just a case study, right? So we pick a particular author, right? So we look at its neighbor. The different color means that they're coming from different meta paths, and you can see that the weight is really very different. Okay. So the next, we are going to look at application on malware detection. Okay. So the question is that how do we represent a program? What is the characteristic to capture in the representation? So we can represent a program by the program behavior graph. Then the question is that how do we distinguish normal program and malware program effectively and efficiently? So we have to do graph matching or similarity comparison. Graph matching is more complicated. A better way is to use this graph neural network to get a graph representation or a graph embedding, and then we can compare the 2 graph embedding to decide whether they are similar or not. Okay, so then in the computer system we have many programs, right? But we can have such a meta path, such a schema to represent each program, right? So a program can fork another program, or he can open an internet socket, and then he can access file. So those process or program can be related in the following way, right? If one fork the other one, that is one type of meta path. If they share an internet socket, that's another meta path, or they share a file. So now we can have define multiple homogeneous graph between the program. Okay, so basically we have known banning program, and then we also have this unknown program which may be malicious, right? So we want to first find the program execution graph, and then we apply neural network, right, to find an embedding of the graph, and then we compare whether the 2 embedding are similar or not. If it is similar, then it comes to be banning. Otherwise, it would be a malicious program or unknown program. So basically, what we do is that once we get a program representation, then we apply the different meta paths to obtain a homogeneous graph. So once we have the homogeneous graph, then we can apply this graph neural network, and we can do it with that, right, with multiple layers, and then we can aggregate across the layer, and then finally we can aggregate across the different meta paths. Okay, So you can see that by doing this search approach that we will be able to identify this malicious program or unknown programs, right? And get better results than traditional graph neural network approach. So the next thing we're going to look at, we still are going to look at the node and link type heterogeneity, but now we are looking at how do we use the attribute of the network node to help us to do even better. Okay, so in here we want to explore content-based correlation between the node, because previously we're only looking at the meta-path relationship between two nodes. Now we're specifically looking at the attribute of the node. Okay, so look at their content-based correlation. Certainly, we still need to consider meta-paths. So now we have basically three layers. So the first layer still is semantic based on meta-paths, right? The second layer is content-based. Okay? And then we can do this with multiple layers, so we can get high order attribute relationship. Okay, so basically the first step is still we want to use the meta-path. Okay, so as we said before, that when we use the meta-path, we'll be able to get multiple homogeneous network. But previously, we applied this graph neural network to each homogeneous network separately, and then finally we aggregate them together. But now we are going to apply to aggregate the different metaverse at the beginning. Okay, so instead of having multiple homogeneous graph, now we actually having a graph, you know, with only one type of node, but multiple type of link, because each meta path really represents a different type of relation. So it's a different type of link connecting the node. Okay, so it's really reflected in how do we construct the adjacency metric. So the adjacency metric now really is the value is the similarity between each pair of nodes over all the meta paths, not just based on one particular meta path. Okay, so this is what we do. So we have this heterogeneous networks, right? Once we introduce the meta path, we get multiple homogeneous network. Then we merge them into a composite networks, right? Which have multiple node type, multiple link type, only one node type. And then in the next step, we even merge the link type into just one. Okay. Okay. So in the next step, when we are looking at content-based correlation. So at this case, then we ignore the different link type. So the two node is connected if there is one type of link connecting them. So the adjacency metric basically is just a binary adjacency metric. If there's one type of link connecting two nodes, then we just connect them. And then we leverage the content-based interaction between nodes and their neighbor for enhanced node embedding. So we use a self-attention mechanism to compute the hidden representation of each node by paying attention to the content similarity. Okay, so basically we have this different type of layers, right? So the first layer is based on this meta-path relationship. And then we can have multiple layers based on the content relationship. So we can stack them together. Okay, so basically, if you look at it, in the bottom, right, this part is semantic based on the meta path, and we can have weight on the different meta paths, and then we can use this GCN on this adjacency metric. Right? And then we can also base on the content, okay, to build a binary adjacency metric, and then use GAT, on this network. And then we can multiple layer of this, right? So if we look at the results, right? So we will do better than conventional neural network, and we also be doing better than what we have talked about in the first part, that we only look at meta paths, but without using the content to enhance the network, right? Okay. Similarly, for the node clustering, we also do better, and we also doing better without consider the content correlation. If you look at some visualizations, right? So you can see that these two different is the number of layers. Certainly, you have more layer, do somewhat better, right? This is 1/4 layer compared with 2 layer. And then this is the conventional GCN or GAT. You can see that it's not as, the separation is not as clear as the one we talked about. And then the AGN is somewhat better, but still is not as good as what we can consider the content-based correlation. And then you can see that the different meta structure have a different weight, right? And also the number of layers. So usually a 4 layer seems to be good, right? So the next thing we're going to talk about is neighborhood heterogeneity. So we talk about that we at the beginning that we reduce this heterogeneous network into homogeneous network. But even for homogeneous network, the neighborhood is not necessarily that similar. Okay, because if you look at the context, okay, for example, the label of the neighboring node, the feature or the relationship, they not necessarily all that similar. And for many applications, the neighborhood actually is quite inconsistent. For example, when we talk about the fraud detection, right? When we construct, when we reduce the network into the homogeneous network, only consists of the fraudster and the normal users, right? The binding users, right? They are all connected, but certainly the fraudster has a very different behavior than a normal user. So if you just treat them the same, then you will not be then you will not be able to detect the fraudster. But even in a less drastic application like this social recommendation, we're using friends to help do recommendations, right? But if you look at your friends, they are not necessarily sharing the same taste on every aspect of product or category, because you may have some friend, they like the same kind of food as you are, but you may like different music, okay? Or they want to read different type of book. So when you use your friends to do recommendation, you have to really be careful, which friend are you going to choose? Okay, so let's look at examples. Right? So this figure is really reduced from the meta paths. Okay, so in the end, that we only have user, but there are 2 types of user. One is the fraudster, the other is the banning user. Right. So the fraudster user is coming pink, and then the normal user is the green one. So you can see that they all connect together. They also, there's 2 types of relationships, right? But you can see that if you want to find the embedding of V1s, right? If you aggregate it all over those green nodes, then you will actually you will dilute the special characteristic of the fraudster node, make it hard to detect. Okay, so we have to really be careful that which user we are going to use to do this aggregation. Also, you can look at that. It's not only their different relation, their feature can also be different, right? So you really need to be careful on the selection. Okay, so what we want to do is that we design a consistent score to filter the inconsistent neighbor and generate corresponding sampling. So we only choose a good similar neighbor, right, to do aggregation. And then we learn the relation attention weight associated with the sample node. So basically, when we're starting with such a network, right, so we have to be able to sample the nodes which are more closer to this fraudster node, right? And then we do this embedding on different relation or different meta paths, right? And then we aggregate them together, and different meta paths have different importance, right? As we talked before, right? So in here, let's looking at the neighborhood consistency. We look at two types of consistency. One is feature consistency, how similar their feature are. The other is contact consistency, is that looking at your neighbor node, that what is the whether their label is the same as yours. Okay, so our focus is on this span reviews, right? From this Yelp data set. So because the Yelp data set is a heterogeneous data set, so again, we have to define meta paths to get homogeneous network. Okay, so this homogeneous network is on review. So we are connecting review together. Okay, so the first type of meta path is the two review coming from the same user. So if you look at that, that consistency is pretty high, because usually if a spammer, most of the review he write is spam, but certainly occasionally he may write normal reviews, right? But if you look at review on the same product, that certainly is a mixture, right? So if you look at a spam review, maybe connect to many banning review. So the label consistency is very low, right? Even if you restrict it to a certain period of time, still it is quite low, right? If you consider all the meta paths, right, together, then still the consistency is very low, right? But even if we're looking at some general data sets, right? For example, like this Corright's publication citation data set, right? That even the feature may not be consistent, may not be that high. PPI, right? So it's a protein-protein interaction network. That feature is really, even if two protein interact with each other, their feature may not be that consistent. And then Reddit is a posting network. Okay, so their label is not necessarily that consistent. Right? So if we apply this approach, then we can do better than, for example, the GraphSage, that is the more traditional neural network approach on detecting the spam. So next thing we're looking at is social recommendation. So we want to explore social link to do product recommendation. But social inconsistency problem may exist because social links are not necessarily consistent with the rating prediction process. Your friends may not like the product exactly as you like, right? So we need to filter our inconsistent neighbor, okay? So let's look at this particular picture, right? So we have three users, U1, U2, U3, right? So U2 has friends U1 and U3. But in this particular case, you can see that U2 has bought product on the sports category. Yeah. And U3 is a friend, but his purchase is more on books. So they really have different interests, right? So U3 is not a good candidate to help U2 to make purchasing decisions, right? U1, although also is interested in this sports good, but he's also interested in books, right? So, but his rating to the product T1 is very different from U2. So in that sense, that is also is not a good candidate for helping in U2 to make purchasing decision. Okay, so usually in this e-commerce thing, we build this type of thing, what we call a bipartite network. We have user, we have item, and the user is connected to the item he's interested in or he has purchased, right? And then we look at other user to get idea to do the next purchase recommendation. And in here, meaning in the social network certainly give us more connection to other people, right? But we have to be careful on the user we choose. Okay, so in here, the main idea here is that when you choose the neighbor, you really have to. So we have to consider a user an item pair, right? So we have to choose user, your neighbors, right, which are more related to the product, right? So to form the embedding. So in this case, you can see we are better than if we look at the rooming square arrows, right? We are better than the traditional neural network approach. The next thing we're going to consider is what we call the fragment heterogeneity. In a graph, we can have many heterogeneous fragments, like motif and subgraph, and they can contain vital characteristics and prominent pattern. This kind of information is not captured during the global summarization process around the node. For example, in the GNN, we do this aggregation around the nodes, right? But then we don't see the big picture. This is just like you only see the tree, you don't see the forest. For example, in this organic molecular graph, right? For example, you can have this carbon ring or things like that. It may have may give you some high-level information. So subgraph can be exploited to preserve high-order structural information. So the analogy of subgraph in a graph is just like object in an image, right? Or a topic in a document. Right? So it is go beyond the pixel in the image or the word in the document. It gives you some higher level information. A graph can contain a diverse set of distinct subgraphs. Nowadays, when we are getting this graph representation, we apply graph neural network method. But before this neural network become popular, what people do on graph is that they apply this frequent pattern mining to find distinguish subgraph in a graph data set, and then using those distinguished subgraph feature as the feature of the graph to represent the graph as having by a set of a subgraph feature, right? And then actually it's pretty successful at doing graph indexing in graph search, graph classification, or graph clustering. So it shows us that the subgraph node can be very meaningful. Okay, so we want to exploit this distinctive subgraph. And then certainly, there are certain challenges there, because we don't want to find any arbitrary subgraphs, right? We want to find subgraph which is discriminatory, okay? So it can be representative to the graph. And we don't really want to rely on prior knowledge because that is too much trouble, right? We want to find an automatic method that will be able to generate a subgraph. And hopefully, this subgraph can also provide some interpretability, okay? So that will be good. So how do we do this subgraph? Get a subgraph. So first we do some subgraph sampling. So we want to generate this n subgraph, right, from the original graph. So it's usually people believe that the node with high fan out maybe is more important, is more meaningful. So we start with the so we pick n node with the highest degree, okay? And then for each node we pick, we use it as a central node and then do a breadth first search. So expand it into a subgraph of some size. And then from this set of subgraph, then we pick the more meaningful one, what we call a striking subgraph, which has more discriminatory power. Basically, we use some reinforcement learning to find the set. Okay, so once we find the set of striking subgraph, then in the original graph, we replace that subgraph by a super node. Okay, so then we can actually also find the super nodes embedding. Okay, and then we use another step, which we call is a supervised concurrent learning. Basically, the whole graph embedding and this subgraph embedding, they should be considered to be a positive pair. Okay, So, I think this is logical, because if the a subgraph is very representative to the graph, right? Then their embedding should be close. Okay, so basically, to summarize what I have said is that we have this graph, right? So we first generate or sample n subgraph, right? And then from this n subgraph, right, we apply this reinforcement learning to select a subset of striking subgraph, and then from this striking subgraph, right, we create this super node, and then we also use this contrast learning to look at the graph and the subgraph pair as a positive pair, right, to help us get a good embedding. Okay, so you can see that by taking this approach, that we'll be doing better than the traditional graph neural network approach. And a logical question is that how big the subgraph should be, right? So we can see that, a subgraph between maybe 5 and 6 is sufficient. We are not really looking at a very large subgraph. Okay, so let's look at some example. For example, for this particular chemical compound data set, there are some of the chemical compound is labeled as mutagenic, okay, and some is non-mutagenic, okay, and then we can find as some important striking subgraph. Okay? And then the other is another chemical data set, right? Chemical compound data set. They are active and inactive component. Then we can also find some striking subgraph. Okay. So the next topic we're going to talk about is temporal heterogeneity. Okay. As we know that, okay, in the e-commerce environment, that we have two types of nodes, right? One is the user, the other is the item, and then the user is connected to the item if it purchased that particular item, or he like a particular item, giving a good rating. And then from this bipartite graph, we want to find other users who have purchased similar type of item that we consider them to be similar in taste. And then we get some idea to do recommendation. But however, this graph actually is not formed in one particular instant. It's actually formed over a period of time, because you see, every edge here is a transaction, and the transaction is occurring at a particular time instant, right? So this really is this bipartite graph representing the user-item relationship, right? It is a dynamic graph. It evolved over time. It continued to add new edges. Every time a new transaction occurs, then a new edge is added. So what it means is that if we do this graph embedding by aggregating your neighboring nodes embedding, if we are doing this kind of operation, then the node embedding needs to be updated continuously, right? At each new interaction. And then there is a problem is that because a node is connecting to many other nodes, right? So when this node's embedding is updated, so what happened to the other nodes connecting to it, right? Because for a node, if the neighbor's embedding changes, right, then it's logical to also, we should maybe also update those the other nodes, right? So otherwise, the early updated node become obsolete because it's not really capturing in the information of its neighbor. Okay. So let's look at an example, right? So example at time 1, okay, only Bob buy a refrigerator, right? So these two nodes are connected, right? So Bob has some information about refrigerator. Refrigerator also has some information about Bob, right? And then as time continues, for example, the Tom by a laptop. Okay, so again, Tom has some laptop information, right? And laptop also has some information on Tom. And then Bill, the middle node, right? Then he buy a refrigerator, right? So then his embedding actually also reflected that Bob's purchasing of refrigerator, okay? Because Bob and Bill now become similar because they all like refrigerator, right? And then when Bill also buy a laptop, then he also connected to Tom, right? Because through the laptop, he also pick up the Tom's information, right? So after this round of transactions, so you can see Bill and laptops, right? They have all the up-to-date information. This refrigerator, although it's connected to Bill, it doesn't really reflect the characteristic, all the characteristics of Bill, right? Also, Bob also is obsolete, right? So he doesn't, because he doesn't have the up-to-date information on refrigerator, right? So there is what we call information asymmetry. Okay, so the question is that how do we design a method to update nodes in both forward and reverse direction? So in a sense that we also want to update the embedding of the nodes when what we previously interacted with when our embedding are updated. But there is an efficiency issue here, right? Because if every time your embedding get updated, you're trying to update all other nodes whose embedding may get affected, that is too much work. So we really need to be very selective on which nodes embedding we want to update. And then there is the issue that now if we look at all our neighbor, when you are aggregating with your neighbors, right? Their embedding all occurring, being updated at different times. So some nodes embedding may be very obsolete. Okay? It's updated a long time ago. So some neighboring nodes, is embedding maybe has just been updated. Right? So the question is that, do you treat them equally or you want to do it differently? You view the more up-to-date embedding to be more important. Okay. So what we want to do is that to develop an embedding model that prevents information asymmetry. So we want to keep a previous interaction node sequence of each node by a previous node window based on degree, in the sense that we do not want to update every possible node which may get affected. We will only want to choose a subset of those nodes. Actually, when we are choosing the node, for example, it is node with which is more important in a sense. For example, the node with larger degree, because larger degree means that there's more people interacting with that node. So the up-to-date embedding of those nodes is more crucial. Okay. And then we also want to update embedding along reverse direction of the timeline. So this is a picture, maybe it's harder to understand. Okay, I just talk about a high level. Right? So we have a user node, we have an item node. When a user purchases item, we certainly want to update both of them's embeddings, right? But we're not only updating in this node, we also updating in the item this node previously we had interacted with, we collect the important one, also updated. So with that, then we can predict that what the next item a person may really want to purchase. So you can see that in here that we compare the approach with other sequential recommendation approach, which basically based on either LSTM or RRM, because we are now handling a sequence, right? So those approach doesn't do that well because those approach basically are sequential approach, but our approach that although you capture the sequential information, but inherently it's a graph-based approach. So we are more able to to capture information from other like-minded users. Okay, so the next thing we're talking about is the structural heterogeneity. Okay, so if we look at this graph on the left, right? So if we do a graph embedding, we are mapping it to some space, right? For example, in the right-hand side, this is a Euclidean space, right? So this is the embedding of those nodes, okay? And then, but we can also map it to a different embedding space. For example, hyperbolic space. In this case, that happen to be those nodes are much closer to each other, right? So that actually is good, right? It's because those nodes form a cluster, right? So we really want them to be close to each other in the embedding space. Okay, so actually those different embedding space have different curvatures, right? And there are different type of curvature space. For example, the hyperbolic space we just talked about, their curvature is less than 0, right? It is good for hierarchical type structure. And then there's another space we call the spherical space. It has a curvature larger than 0. It is good for cyclic type architecture structure. And then the usual space we use is what we call the Euclidean space, right? That curvature is 0, right? It is good for grid type structure. So for large and complex graph, we don't have nicely regimented structure. That means that we don't have a uniform curvature we can map into. And so we require heterogeneous curvature spaces for embedding. For example, if we look at knowledge graph is a very complicated type of graph, right? You have all type of information there. So if you look at it, for example, we look at George Lucas, right? For certain information about George Lucas, that may very well look like a hierarchical structure. For example, we say what movie may he have write, right? And then this is started by which actor. So this is very much a hierarchical structure. But there are other information really coming back more like a cyclical structure. For example, George Lucas has directed a movie called Star Wars, and then he has a certain character there, Harrison Ford, and then there are certain stars there and then written by this George Lucas, right? So you have all these different type of relationship exists, right? And then some relation is better to be represented by hyperbolic space, and some of them may be better by Euclidean space. Okay, so what we need to do is that we have to map the heterogeneous graph entity and relations into a mixed curvature product embedding space. So we have to define and construct a mixed curvature space through a product manifold combining multiple single curvature space. So we really need to combine these three space: spherical, hyperbolic, and Euclidean space known as a Cartesian product, right? And then to capture, and then so we can capture the intrinsic heterogeneous structure. And we want to adaptively integrate the heterogeneous relation context in the mixed culture space. This heterogeneous relation, as we talked about before, right? That is the critical thing that we have to capture in the heterogeneous network. But now, in addition to this various type of relation, right, which is captured by metapaths, right? And we also have to worry about this mixed culture space. Okay. So first, we need to capture the relational context because it can improve the embedding quality and may have also different importance. Right? And then so we propose a GNN-based embedding updating method to update the embedding of entity-head relation by selectively aggregating the relational context in the mixed curvature space. So now we have two factors to consider. Right? One is the relation context, the other is the curvature space. So if we do that, right, so we can see that performance will be better than some other neural network which are only in the Euclidean space. Okay, so you can see the improvement can be quite large, right? So today we have talked about various types of heterogeneity in the network. I mean, we covered now 5 different types of heterogeneity, right? The node and link type heterogeneity, that is the most commonly you see. Because most of the network really consists of multiple node type and link type. And the neighborhood heterogeneity, even for homogeneous network, your neighbor is not necessarily consistent, right? Because the neighbor may have may be different from you on different aspects. And then so depends upon the purpose of what you are trying to do, right? You may want to select different group of neighbors, right? And then we also talk about this fragment heterogeneity, which will give you this higher level semantics, right? And then temporal heterogeneity, right? This is very important in dynamic network because we don't have the complete network at the beginning. The network really grow over time. So we don't have all the neighbor at one time, right? When we trying to apply the GNN to do this neighborhood aggregation, the neighbor keep on coming over time. So the question is that how do we really handle that problem, right? And then we also talk about, in the end, we talk about the structure heterogeneity. The structure heterogeneity certainly I talk about this multiple curvature space for embedding. So we also have looked at many different type of application, right? So we have looking at this social recommendation, and then we're also looking at sequential recommendation. We're looking at malware detection and fraud detection, knowledge graph. So certainly this type of heterogeneity reflect differently for different type of application. In certain type of application, in one type of heterogeneity may be more serious than the other. Okay, and we examine various ways to address this network heterogeneity on graph neural network. Okay, so this is the end of my talk. Thank you.
So thank you very much, Dr. Yu. Do we have any questions? Yeah, so if this was a room at this point, we would all be clapping, and I'm sure the audience is. Any questions? Okay. So in that case, I'll first ask you a very general question. So you gave us an overview of what what can be done, what the issues are, different types of heterogeneity, and how to model things, and so on. So looking forward, what are the open problems, the biggest challenges in the graph neural network area?
I think this heterogeneity is an important issue, so we need to study it further. Certainly, the heterogeneity also coming from different application, because different application may bring in the new type of heterogeneity. So I think this heterogeneity also is also closely related with real application. And I think there's a lot of opportunity to study how to handle this heterogeneity because traditional neural network is generally assuming this homogeneity and smoothness property.
Okay, yeah, I would wholly agree with that. Are there certain types of heterogeneity that you think that GNNs are the most, easiest or can represent well? And are there cases where there are still inherent technical issues that makes it hard to, within the different types of heterogeneity?
I think certainly, for example, we can map certain heterogeneous network into homogeneous networks, right? To take advantage of GNN. But we also need to be careful when we are aggregating the neighbor, because the neighbor is a complicated issue, right? Because not all neighbors are helpful. So we really need to be depends upon the application. We really need to be very selective on aggregating the neighbor.
Yeah, that's true. And then, so if we are, we are managing the heterogeneity in this way, and in some sense, there is some amount of loss in the information going on where, and is there some post-processing or something that we need to do or some checks to make sure that we haven't actually lost things and we are, representing the heterogeneity is actually respected and preserved in the decisions that are being made?
Yeah, I think this is a valid question, right? So when you are being restricted, you may be too restricted, so you get rid of some neighbor which information is valuable, right? So there is a trade-off, right? You have to know what so you need to know how to weigh the information, right? Yeah. So otherwise you are filtering out too much information, right? So I think that that there is a clear trade-off there.
Mm-hmm. And then, so in the recent years, there have been like variants of graph neural networks that you're, aware of. The most interesting, interesting ones, are the common ones would be like graph convolutional networks. Then there were graph attention networks, graph recurrent networks. Do they follow in sort of a parallel line to the other research, to just the normal neural networks, and have similar characteristics, or are they different? Any thoughts on that?
Yeah, certainly. No, you put attention in the sense that you are also treating the neighbor differently, right? But we are more specific on the heterogeneity, and then trying to do it in a more effective way.
Yep. Anybody else has any other questions? So I'll ask one more. So what about the, the other characteristics and issues? So for example, as you are well aware of, issues, let's say like robustness, and because of the modeling that's going on and so on, how easy or hard is it to create adversarial attacks and so on, and also the things like interpretability or balance, bias and fairness. So in any of these three topics, you have comments on where the field is going and what the issues are.
Yeah, I think those are all important issues, right? Because one of the things with the deep learning is the interpretability, right? I think robustness is actually is not as bad, but certainly you can have that adversarial attack, and then there's a lot of tension on that, right? So there's a lot of room to work on those aspects.
Yeah, but since you are an expert and you've done a lot of work, are there special things that make the problem harder for graph neural networks, or is it easier, or is it about the same?
I think interpretability always is more difficult at this graph neural networks, right? Because but by doing some things, for example, like subgraph or metapath, it gives you some level of interpretability. Mm-hmm. Because you are learning certain type of relationships is more important, right? So they give you a level of interpretability. Also, subgraph sometimes it has certain meaning there, right? So it can also give you more interpretability.
And when you're talking about subgraphs and so on, that sort of begs the question as to how important is it to identify features, so to say. So you're from a data mining community. I've done some work in data mining. So feature engineering and creating these subgraph features was in some sense harder than, let's say, in text, where you could use words as features and things like that. So in this case, where do we stand with respect to the importance of feature engineering, or is it that this is a deep learning method and it just figures out things themselves? We can just throw everything in and it works.
I think the good thing about deep learning certainly is that we don't need to worry about feature engineering, right? So that make the life a lot easier to some people, right? But even we talk about subgraph, we still are not trying to do it through to have the expert to help you find the subgraph, right? We want to use this automatic method to find subgraph. But because subgraph is a structure, so if you say this is important, you look at it, you may get some feeling, right? So you look at it, it may give you or help you interpret that why you are getting better results, right? But we are not really trying to do feature engineering.
Mm-hmm. And so in the if you go to attention models. So in NLP and so on, if you have, we know that we have these attention models where we can say, okay, these parts of the sentences are more important and so on. So there is an analog in that you have graph attention networks. Now there it's, so some people have used the attention model as interpretability. So, this is the most important part of the sentence, and that is why we are making this decision. In the graph attention networks, that brings us to, okay, these are the parts or subgraphs that we paid more attention to. Does it get easy to interpret those things, or because it's a graph, it's not a word per se, it's sort of very hard to figure out what the pattern is?
I think that if you pick out the words, right, I think everyone know.
Right.
Any common people can see, okay, this word is important, or
right.
whether this word makes sense or not. For example, if we use, if our graph is chemical compounds, right, you identify some subgraph, it is still meaningless to most of the people unless you find a chemical expert. He may say, oh, this is a carbon ring, it makes something. You know what I'm saying?
Yeah, so in that sense, it's almost, harder. Just like feature selection was harder in large graphs, so we are having sort of similar issues with respect to attention. I will put my power on, because otherwise if my computer goes down, the whole meeting might end. Any other questions by anyone? So thank you very much. Then, Dr. Yu, it's a great learning experience. Thank you for spending your hour and a little bit more with us. We really appreciate your efforts. Thank you very much.